thank you very much for coming to this talk, where we are going to do things with machine learning agents that you've never seen before, hopefully. My name is Alexander, yada, yada, yada. Long surname, not interesting. I have a couple of hobbies. I really like bouldering. I like to play Dungeons and Dragons. And I'm a huge video game nerd. Are there any other video game nerds in the audience? Good to know that at least some of my jokes will land. I'm a consultant at J-Driven, a small consultancy in the Netherlands. And currently, I'm consulting routescanner.com, a door-to-door pathfinding for logistics, for container logistics in the Netherlands. Are there by any chance CEOs of multi-billionaire retailers in the audience? Really? I really want to talk to you afterwards. All right. So, why this talk? Quite some time ago, I was reading all about machine learning, left and right, machine learning this, machine learning that, AI this is going to revolutionize everything. Well, we saw our keynote where we are right now, and then I decided, maybe I should do something with this. Maybe I should at least know a little bit. So then I went online, you start Googling Stack Overflow and everything. And then you realize everything up to that point was, all of the tutorials were a little bit boring. I'm a gamer, so my attention span is around 5 seconds. And if I don't get a dopamine hit within those 5 seconds, then I'm gone. So yeah, trying to identify cactus in an image and training a machine learning model to do that was not very interesting to me. Then that's why I discovered that I could do it in a game engine as well, in Unity. And I hope maybe I can inspire some of you that want to go into machine learning today to do the same. Or if there are experts, machine learning experts in the audience, maybe they can revolutionize the game industry because it does need a little bit of a shake-up right now. All right, so machine learning in games. We all know what machine learning can do outside of games, right? From self-driving cars to image recognition, speech recognition, writing complete stories for us and things like that. But not a lot of people talk about machine learning in video games. Does anybody of you have any idea how machine learning can be used within a video game?
Animation.
Sorry?
Animation.
Animation, yes. It's not one of the ones I've listed, but yes. Yes? Enemy AI, well, perfect. So NPC, and NPC is a non-player character within the video game. And indeed, there are a lot of games that are experimenting with using machine learning agents to fuel the actions of their AIs. And there's a game called Planetary Annihilation. I don't know if anybody has played it, that actually uses neural networks within their game for their standard AI. Anything else?
Map generation.
Perfect. Have you seen my slides? Procedural content generation, exactly. I think Minecraft. So machine learning models can train to basically create the perfect world for you. There's a game called Source of Madness that is generating NPCs, so the adversaries complete through AI, and they all look super goofy, like Spore. I don't know if anybody of you knows that game. Or there are other games that generate weapons for the player based on the player's preferences during a play session. And that's very interesting. Well, maybe 3 for 3, anybody? Yeah? Storytelling. No, I'm sorry. Player simulation. This one is probably the one you've heard before. An AI beat AlphaGo, the best AlphaGo master or the best chess master. A couple of years ago, there was OpenAI trained 5 AI agents to play Dota 2, a very popular online game, and they actually beat the world champion in a game of Dota 2. And of course, the AIs train against themselves, so they are simulating players to become better. And then finally, we have automated game testing, which is basically, for example, anybody that doesn't know Candy Crush. Good. Candy Crush uses AI to test their levels, basically, and make sure they are as addicting as possible. So yeah, then we have machine learning in Unity3D. Anybody here that has played with Unity3D before? Made things with Unity? Perfect, perfect, nice. Unity, for the ones that have no idea, is a game engine, or as they want to call it nowadays, a 3D development engine. It can be considered a market leader, especially on the indie development market. So on the AAA, it's not really up to par to Unreal yet. You use C# to script in it. Right? This is the moment where I was expecting a couple of boos or some people walking out. And one of its biggest strengths is the build once and deploy anywhere credo. So you have one code base, you build once, and you can deploy to Android, Windows, Samsung TVs, etc., 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 which works pretty good. And some time ago, they decided, OK, this machine learning thing, we probably want to do something with this. So they created the ML agents package. That's open source. It's built on top of PyTorch. So it basically uses PyTorch as its engine. There we go. It supports reinforcement learning algorithms and imitation learning algorithms. It contains a low-level API and a more accessible entry point through the Unity editor, which we'll be using today, which is also kind of nice. Then you kind of can treat PyTorch as a black box. You know, we love treating things as a black box. It was released in 2017. It was being updated regularly up until a couple months ago. Maybe some of you read the news, but Unity has been going through some restructuring and some issues past couple months, but they have promised that they are going to continue with the machine learning package soon, TM. All right. If you want to get started with this, it's actually pretty easy. You go to the Unity website, you download Unity. You go to the Python website, you download Python. Versioning is important, so make sure you have 3.6.1 or higher. Not too high, by the way. And then through the package manager, which is like a Maven or a Gradle for Unity, you can basically install the machine learning package. It's a preview package, so you need to enable preview packages because it's not officially released yet. And then it installs it in your Unity environment. You can go. And finally, you need to install the machine learning Python packages through some commands. This can also, of course, be found on their GitHub if you look for it. So how does this work? We have the learning environment, or our academy, you could say, which is Unity. Then outside of Unity, we have a little server that's going to be running with our Python trainer, well, basically PyTorch, with a little bit of Unity sauce over it. The Python trainer is going to be talking to a Python through a Python API to Unity. And basically, what's going to happen now is Unity will be collecting all kinds of numbers, shoving them towards the Python trainer. The Python trainer is going to be like, that's interesting, and send numbers back. And that is what you're going to be seeing in the Unity editor. So yeah, this is still fairly simple, I would say. Now, how does the learning environment look like? There you have agents, or I mean, since you're going to be doing it yourself, awesome agents, because everything we do ourselves is awesome. So we're going to have awesome agents. Agents are basically characters within your game or game objects within Unity that collect observations and take actions. So they're going to be collecting numbers, and they're going to be acting upon numbers that are fed through PyTorch, through the Python server. Those are always have a behavior, and that behavior basically is a set of methods, functions that collects those observations done by the agents or sends the actions to the agents. And then they go to the communicator, to the trainer. Of course, it's also possible to not connect to a trainer. At some point, you'll have a model, a neural network that's going to be working perfectly. And then you want to use inference. And then you can basically infer, put a brain on the behavior and say, OK, this is the brain that needs to be controlling this agent, and that is what it's going to do. But I'll show you all this in a little bit. And finally, you have heuristics. That means if you want to debug your agent, you can create the controls yourself, and then you can just debug your agent, move him around, make sure that he does what he's supposed to do. All right, so there are two training methods. We have reinforcement learning, and we have imitation learning. I think they're pretty self-explanatory, right? Reinforcement learning, you punish or you reward your agent when he does good things or bad things. And imitation learning, well, it tries to imitate the demonstration set as good as possible. There are multiple supported algorithms. For reinforcement learning, you have proximal policy optimization, PPO. I don't know if anybody has used PPO in one of their projects or something alike. It was released by OpenAI a couple of years ago, and it's a very cookie cutter, just gets the job done algorithm. And then you have the soft actor critic, which is which is off policy, which can also learn from its past experiences. That means that it generally learns faster than a PPO algorithm, but it requires many more model updates to learn. So it's a little bit of a balance. And for imitation learning, we have behavioral cloning, which tries to clone the data, the base set, as good as possible. Or when you don't have a lot of, you don't really have a good base set, you can use generative adversarial imitation learning, which is going to take an adversarial approach to the agent and try to teach it that way. Our agent is going to be walking around, making observations, things like that. And there are certain observation types that can be done. First, vector observations. Vector observations are basically float numbers, floating points. Unity works with floating points mostly. So there will be, so when you look around, your position, your rotation, your scale, distance to a certain object, those can be vector observations. Visual observations are really, okay, what is this camera or this set of cameras seeing right now? So if you, and that is how you can filter out black pixels from your screen and things like that. And finally, raycast observations will be where you can shoot a raycast, a laser beam, so to say, like this, if you can even see it. Oh, nice. And then it registers what it hit from point to destination. And that is what you're going to be feeding the algorithm. So that is everything that the package supports right now. But for today, all the demos I've prepared will be focusing on reinforcement learning and PPO, so the proximal policy optimization, and everything will be done with vector observations. So let's get ready to training our agents. I trained everything on my own PC at home with an old graphics card. So it was a little bit tricky. Sometimes I had to leave my PC for 3 days to get the result I wanted. But yeah, you kind of built a relationship with your agents. You're like, oh, well done, little guy, good job. So let me show you, let's show you what I've done. So first, you're going to be designing your agents. An agent is going to do an observation. Based on that, there's going to be a decision, then an action, and then there's going to be a reward or not. That depends. An observation can be a position, a rotation, any float number, basically, in our case. A decision has a decision period, so not every academy step, which is 1 frame in the game. So hopefully a game is going on 60 frames per second, so that would mean 60 academy steps per second. But you can say, okay, my decision period can be spread out a little bit more. So if you set your decision period to 5, which we will have in all the demos, that means that every 5 academy steps, a decision is going to be requested. And the decision can be basically, okay, feed me a random number or feed me the best possible number from the Python trainer. And then you can say, hey, can you take actions between the decisions or not, which we always have set on yes for the demos. Then you can take certain actions, which can be continuous or discrete. A continuous action is basically a list of float numbers, which you can use to move or rotate your character or whatever. Or discrete actions, which can be used to branch out your actions. So if you want to be able to move and jump, you can use the discrete actions to branch out multiple actions. And finally, we're going to be giving a reward, which is any number between -1 and 1. So -1 is the fail. Well, the epic fail condition, 1 is the epic win condition, and 0 is a boring draw. So the first one, the pirate and his treasure. Yeah, you see a stickman. You have obviously no idea what this represents. They should make it better. So we have a pirate, we have a treasure, and everybody knows pirates love treasure, right? So we want him to move towards the treasure. If he reaches the treasure, we're going to be giving him some candy. So a reward of 1. We're going to have a training area. And if he dares to move outside of the training area, we're going to punish him. We're going to give him a reward of -1, basically. And that is how we hope to train this agent. The observations that we'll be doing are his position and the position of the treasure. And finally, the actions we'll be taking are movement on the x-axis and movement on the z-axis. So we'll be moving on a 2-plane axis, 2D, basically. All right. So this is the Unity editor. This is our pirate over here. Anybody has a cool name for our pirate?
Jack Sparrow.
Jack Sparrow, yeah. Could have expected that one. All right, our pirate Jack is here. If you look at to the right, you can see his parameters, basically. I hope it's very visible. Well, a screen like that should be weird if it wasn't. As you see, we have vector observation size, which is 6. So the position, a positional vector in Unity is a set of 3 numbers, x, y, z. So we have 1 for his position and 1 for the treasure position. So 2 times 3 should still be 6. And then we have 2 continuous actions that we're going to be feeding this agent, 1 to move to the x-axis and 1 for the z-axis. We have a max step of 5,000. That means that after 5,000 academy steps, if you didn't reach a goal, we're going to end the episode and we're going to reset it. So, because then somebody probably went wrong. And you also don't want them to continuously trying endlessly. We're going to be using our CPU for training. This might sound weird, and I can't believe I'm saying these words, but my GPU is too new. Because I'm using a little bit older PyTorch version, which doesn't support the latest CUDA versions that the newest GPUs come with, unfortunately. So we're CPU bound, but should be fine. All right, if you look at the code of this pirate agent, well, you'll inherit from an agent that you get from machine learning package, and basically you'll be overriding a couple of methods from the package to do things. So you're going to have an onActionReceived method that you're going to override, which is going to be 2 numbers, 2 float numbers between -1 and 1. And you grab them, you map them to whatever you want to map them, and you move. And we're going to be moving our agent based on those new positions. Then we have the collect observations method, where we just add the observations we want. Fairly simple, I would say, fairly straightforward. Then we have the onEpisodeBegin. So every time an episode begins, for example, when we reach our goal or the wall or the max steps, this will be fired, and we're going to randomize the position of the starting position of the pirate and the chest. Otherwise, it would just learn to go to the right. That's a little bit boring, so we want him to work a little bit for it. Well, the heuristic function that lets you program the controls. And then probably the most important one is the onTriggerEnter. This is a Unity message method. And when 2 physics objects collide, and one of them is a trigger, mark the trigger, this message is fired. And if the other object is the goal, so the chest, we're going to set a reward of 1, and then we're going to end the episode. And if it's a wall, we're going to set a reward of -1 and end the episode. All right. So we're going to open our command line and then give a run ID of yar har jack, something like that. OK, we get beautiful ASCII art. And then it tells us that it's waiting for input. So start by pressing the play button. All right. Then we can press play. And as you can see, little Jack is trying to find the chest. Well, of course, this is going to take quite some time like this to train him to find the chest. So, but we have a little bit of a workaround. So let me stop this. All right. Then we can basically turn on these. And now we have a lot of clones of Jack in his learning environment or training area for the chest. And then we can basically do this, and then we're going to tell it to resume training from a previous run. And then we can press play. And then here we go. We have a couple of Jacks running around trying to find treasure. And that is how you train it, and that is how my computer was looking like for an hour. What's pretty cool is here you can see that it resumed training from step 2.7k. When it reaches that, there we go, step 50k, it tells you what the mean reward is of your training session. And if things go wrong, if things go right, sorry, they went wrong so many times. If things go right, it should grow. So the reward should get closer to 1 at some point. So there we go. Not entirely right now, but it will get there eventually. All right. Let me stop this again. All right. Let me stop this. So once, let's say, I mean, we can train it here. It takes a little bit too long, but once you've trained your agent, you can go to the results folder within your Unity application, and here you're going to see Yarhar Jack. That is your run ID. And then here you're going to see an .onNX file, which stands for Open Neural Network Exchange, which is an open standard to store neural networks, basically. And what you can do then is, let me disable these all again. Here in your agent, you can assign the neural network. I have some pre-trained, of course. And then if you press play without connecting the Python trainer, it's going to infer from the neural network. And hopefully, he will still behave. There we go. And then you can see our pirate slowly trying to reach the chest, very slowly. So yeah, like this, you can do some basic training for your agents. There we go. Took some time. A little bit of clap for Jack, maybe. Thank you. And that is how Jack finds his chest. All right. All right. So that is one. Then we have, everybody knows that cool people don't look at explosions, right? Anybody that disagrees with this statement? Whew, good. All right, so cool people don't look at explosions. So we have a stick person. Now we have a cool stick person. We're going to be spawning a barrel, and the barrel is going to explode after 5 seconds. If it's looking at the barrel when it explodes, that's a punishment. But if it looks away from the barrel before it explodes, now that's candy, right? So that is what we are going to try to achieve here. So observations. It's a little bit less. So we are going to have the barrel position and the position and rotation of the cool person. And then when it comes to actions, we're going to be feeding him only one action, and that is to rotate on the y-axis, so basically turn around. And that is all that we're going to do for this one. All right. And it should be here. All right. So again, we have our training area. If you look at the, we have a max step of 1,000 because it only takes 5 seconds. After 5 seconds, the barrel will explode, so it doesn't really need to stay and try to do things much longer after that. Space size 10, so we have its position 3, the barrel position another 3, and its rotation. Rotation is 4 numbers. It's a quaternion Unity. Anybody worked with quaternions before? My condolences. And one action, we'll be fitting it one action to rotate on the y-axis. All right, and then, of course, if we start it up, so ingredients, learn, and then run ID, let's say, super cool, something like that. All right, so now it's waiting, and then we can press, and there she is. And she's so cool that she walks on water, of course. And then you can see here a little debug thing I've added to look to see how cool or uncool it is at each explosion. So yeah, and now it's basically training. So let me stop this again. All right. If you look at the code for her, a lot of things are actually pretty similar with our Jack pirate. So the only action we receive is rotation the y-axis. So that is also exactly what we do. We're going to be rotating on the y-axis. We feed the 3 observations, the 10 float numbers. And when it's exploding, wait for 5 seconds, we explode, and then we determine what the cool factor is. And we do that by, we calculate the directional vector between the person and the barrel. And then we look at where she's looking, so our forward vector, and then we calculate the dot product between the two. If the dot product is, if they're looking exactly, if they are the same, it's going to be 1. If they're exactly opposite, it's going to be -1. So we basically flip it to, if she's looking directly, it's going to be -1. And if it's looking exactly the other way, it's going to be 1. And that is also what we're going to be feeding it as a reward. And then, of course, you can, again, so train this much, much faster by duplicating your training environment. And now you're going to see explosions all around. And I did promise explosions to a lot of people, so here you go. All right. And yeah, this took a little bit of time to train as well. You can see a little bit of a stutter between the steps, and that is at some point the buffer, the decision buffer, or the observation buffer gets emptied and is sent to the trainer. And the more training agents you have, the longer that takes. All right. And of course, it's also nice to see how it looks in the end. Let me stop this again. There we go. And hopefully, again, there we go. Explosion, and she looks the other way. And it's, of course, much cooler if you look at this like this, right? Just like in the movies. All right. So, but we can go further. Any Harry Potter fans here? That's not a lot, actually. Anybody that has played Quidditch before? It is an actual sport, by the way, but we're going to be playing Quidditch. Well, not with full teams of 8 versus 8, I don't remember, but only the Seekers. So we're going to have a Gryffindor Seeker, a Slytherin Seeker, and the Snitch. But we're going to have 3 agents and 2 separate agents. So the Seekers are going to be using the same behavior, and the Snitch is going to be using its own behavior. So again, you have no idea what this means, right? What this can possibly be. No, here you go. The Seeker wants to find the Snitch, and the Snitch wants to bail. It just doesn't want to get caught. I'm pretty sure those are the rules as defined in Harry Potter. So if the Seeker catches it, that's candy for the Seeker, and that is a punishment for the Snitch. And if this Snitch flies around long enough and doesn't get caught before the end of the training session, that's candy for the Snitch, and that is a punishment for the Seeker. And then we have our training area, of course, and then if they try to move out of the training area, that is no as well. So what observations are we going to be making? So the Seekers are going to be observing their own position and the position of the Snitch, and the distance between the two. We need the distance because we're going to be rewarding the seekers for getting closer to the snitch. Every step they get closer. And then the snitch will be needing its own position, that of the seeker, and again the distance, because it's going to be getting rewarded for moving further away each step. And then it's going to be looking at the walls, because the snitch is not allowed to fly outside. The reason we're not adding the walls to the seekers as well, or the magicians, or the wizards, what are they called in Harry Potter? Is because, well, they'll be following the snitch. So if the snitch doesn't go out, then they shouldn't go out as well, hopefully. The actions they'll be going to be taking are the same as the pirate, but this time also on the y-axis, so they're going to be able to move up and down. Quidditch is a three-dimensional game, and the snitch is going to be doing the same, basically. Oh, I'm going too fast, because I have to show you how it works. Or how it doesn't work. Spoiler alert. All right, so this is our environment. Red is Gryffindor and green is Slytherin, for the people that have never watched Harry Potter before. Again, if you want, you can duplicate the training area. So to speed this up. This one took a lot of time to train, I'll tell you that. All right. So if you look at the code, for example, of the agent, again, we receive the 3 actions, and we make him fly, or her fly, on any direction. And then we force him to look at the snitch to make it look a little bit fancier. And then every time it gets closer to the snitch, it actually flies close to the snitch, we reward it a little bit. We drip feed it some candy. Yeah, the observations, we calculate the distance. What's important to know, and that this is also for all the other ones, always use the local position in Unity. The local position is relative, its position relative to its parent. If you use the world position within Unity, that means it's going to be relative to the 0, 0 of the world, and that means you cannot use multiple training areas within the same scene, basically, because, well, everything is going to be relative to the world and not to its own training area. When the episode begins, we put them in the middle. Heuristics, not interesting. If you hit the wall, we end the episode basically, and we say this is not what you're supposed to do. And if it hits anything else, for example, the other seeker, we give him a slightly punishment, because as far as I know, it's not necessarily not allowed. It's just frowned upon. I don't know. And if it hits the snitch, we do some debugging things. We give a reward of 1, and then we end the episode. And we tell the snitch that you lost, basically, because it got caught. And if you look at the snitch itself, it works pretty similar. You know, it also moves those 3 dimensions. But if it reaches the second to last step, we reward it because, well done, you managed to dodge the seekers long enough, and we reward it for actually flying further away from the seekers. All right, so how does this look? I can probably do this faster now. How about... There we go. Great. It's training, or it's waiting to be trained, and then here we go. Well, our beautiful yellow line is the snitch that continuously flies out of bounds all the time. And then we have the others trying to find the snitch. As you can see, this is going to take some time until they start to realize, okay, maybe I shouldn't move out of bounds. Maybe I should stay here. Oh, maybe I should not get caught, and things like that. All right, let me stop this again. And then we can, if we press play now, there we go. There they are, trying to catch the snitch. I'm taking bets, green or red, whatever you want. And as you can see, they're trying to catch the snitch. The snitch is just a little bit slower than the wizards to give him a little bit of a chance. And there you go, Gryffindor caught the snitch the first time. and the score is 1-0. What's interesting to see is, I think 1-1. I think I was teaching this for maybe 1 day, something like that. And because I'm not randomizing the starting positions, the snitch taught itself to always go to the right upside first. So that was very interesting for me to see. Because apparently that's the best position, or somehow it always started going that way, and then it didn't learn that it can go some other way as well. Yeah. But yeah, as you can see, this is a match that rivals the Champions League finals, in my opinion. Great. We stop this. All right. OK. Anybody that has never seen The Matrix? Good. Oh, a couple of people, I think. So in The Matrix, there is a scene where Neo, our protagonist, dodges bullets in a superhuman fashion, so to say. So I thought, I mean, if he can do it, my agents can do it as well. So yeah, we have two characters in this scene. Now you know which one is which. We're going to have Agent Smith shooting, and then we have Neo on the other side with the sunglasses trying to dodge the bullets. So yeah, I mean, this is going to be self-explanatory, but if the bullet hits him, that's a punishment. That's not supposed to happen. Also, what's not supposed to happen is that any joints hit the floor. So the only joints that are allowed to hit the floor are his feet and his hands. And then if he manages to do that, and then do a nice trick, the bullet flies behind, and the bullet hits the wall behind him, then that is candy for our agent. The observation we'll be making is the bullet position and the nozzle position, so he knows where the bullet is coming from. And then we have 182 observations in total, which are basically the joints of his body. So which direction are the joints facing, the average body velocity, the rotation deltas of the joints, the strain it's putting on the joints. And maybe the more game development people here already understood what Neo is going to be. Is going to be a physics ragdoll. So he's going to be a fully physics controlled character. And the actions we'll be taking in basically is every single joint he has, we're going to be giving it a certain rotation and a certain strength so that he moves it to a certain degree. So yeah, and then yeah, we have a ragdoll, which is going to do a lot of weird things for a long time. And then we have to train him to be as cool as Neo. So that might be interesting. So let's see. So we have no, don't save. All right. So I mean, this would be fairly known by now. Here we have our derpy Neo with the cool sunglasses, and here we have our Agent Smith. It wasn't Agent Smith that shot him up there, was it? It was another one. I don't remember the name. But Agent Smith 2.0. And then it's going to be shooting. If we look at the code, and now this one is a little bit more advanced, you could say. On the beginning of the episode, we reset the whole body, so it goes in a T position. The observations we'll be collecting is, as I said, all kinds of velocities we can get from the body parts and rotations. And we have placed an invisible cube in front of him that moves, that is the average position between all the joints, so that we know that, and if this cube is parallel to the ground, then we know that he's probably standing up, right? So we also collect that as an observation. And then for each body part, we collect the strain the rigid body is putting on the body part. So how much it's straining him, so that he doesn't do like weird things, break his neck, things like that. And then, of course, we add the bullet position and nozzle position as observation. And then the actions we receive, there are 27 in total, are basically all things that we map on the joints. It's to set the target rotation for the joint, and that means that we're going to tell the joint, okay, maybe if your hand is like this, move it like this. and then how much force we're going to give the movement. And then we're going to be rewarding him basically for standing upright as long as possible, so that he doesn't immediately fall over. And then we're going to be rewarding him for dodging the bullet. And the ground check, of course, if he touches the ground with anything but his hands or feet, that is immediate no. All right. So here we go again. How about we live in a simulation?
Red dress.
Red dress, yes. Oh, maybe that's one better. Let's do that. All right. People that never seen Matrix are like, red dress? All right. And now you're going to see our derpy Neo raving like a madman. So, yeah, I mean, anybody can already see what's happening here? It's falling on the ground immediately. He doesn't even know how to stand yet, right? So if I slow this down a bit, here, you can see that immediately he falls down on the ground. So yeah, this took a long time to train before it even started standing up, and then another long time to train until it started dodging bullets. I can tell you, with the energy prices as they are right now, but after a lot of blood, sweat, and tears for Neo over here, he managed to do something. And that something looks like this. There you go. And like this, he manages to dodge the bullet. Hopefully. There you go. So, and when I saw this after 2 days of training, I was like, why did I let him touch it with his hand? He outsmarted me. So yeah, because he's allowed to touch the ground with his hand, he realized that, maybe I can just do it like this. And then he did. And then I was like, do I try to do it normally, like Neo did? Also let him, or do I keep it like this? And then, this was way too funny. But yeah, if you would want to do this the Neo way, with swing arms, then I think you really have to anchor the feet, that the feet cannot fall over. Because a rigid body, a physics rigid body within Unity still tries to follow the rules, the physics rules. And what Neo did in the Matrix wasn't necessarily possible. So I think if you anchor the feet, then you can get a little bit further. All right. Oh, we are back at our kissing footballers. All right. So I have a last one for you. Any heavy metal fans here? Okay, you're going to have a blast in the upcoming minutes. The rest, I'm sorry. Yeah, I'm a huge metal fan myself. I also really like going to metal concerts and, go to the mosh pits and headbang. And I was like, it has to be possible, right, to teach machine learning agents to headbang. Yeah, I bet you never thought of that one before. So yeah, then I'm not going to go into too much detail on how I did this. But if we start training, and how about, there we go. And then we train. Okay, you're going to see them all break their necks and their hands and everything. As they're trying to train to see, okay, how am I going to headbang on this music? All right, but that's not very interesting. The much more interesting part is when they actually do it. All right. And 3, 2, 1. So what's happening here? The quick gist is we have like a metal factor in the scene, Thank you. A metal factor in the scene, and they react to that metal factor. So as you can see now, this is not very metal, what you hear right now, so they're not headbanging. So they're waiting slowly, maybe a little wobble, like, come on. And then finally, once the metal kicks in, yeah, you can see the in unison, like it's supposed to be headbanging to the music, right? And I mean, if this is not the best thing you can do with machine learning agents, I don't know what is. All right, there are 5 minutes left. I really thank you for being here for, obviously a not very serious talk, I would say. I hope I inspired some of you to give this a try, or maybe to, if you're very proficient with machine learning, to go and give this a spin and see how you can revolutionize the gaming industry. Unfortunately, I cannot share the code because the models and the 3D models I used are bought. So I'm not allowed to put it on GitHub. But if you really want to see the code, just ping me on Twitter. That's my Twitter handle. And then I'll just send you the code without, stripped down. So yeah, thank you very much. And if there are any questions, now is the time. Yes?
Can you combine multiple training? Like, could you have headbanging Quidditch players?
Yes. Yes. It's not very effective. I tried it. But yes. Any other questions? Yeah? Sorry?
Does it allow you to
I haven't tried, but they say that it's possible. But then you probably have to start 2 different sessions, Python sessions on the back. Yeah. Oh, yes.
Since Unity can compile most to any platform, do you also need Python runtime or Python on the device itself to be able to run these agents?
No, once they are trained, you don't need Python anymore.
Okay.
But you do need Python to train them. And you don't necessarily need the Unity editor to train them. You can also train them, headless, if you would like. Any other questions? Once, twice? Thank you.